Wow, great talks. So after these great nanoscale techniques, I'm just gonna take people probably back to the a bit over to the potentially millimeter scale realm. How's the presentation coming through? Is it being
looks
dropped?
good? Yep, you're good.
Cool. Then I'll go on. So this study is part of my PhD project exploring novel analytical methods and sampling methods for igneous age dating of shergottites. So igneous radiometric dating is done through one of the following three sampling methods. So we have bulk sampling, which requires 1 to 2 grams of bulk rock sample crushed up and processed through mineral separation and handpicking before dissolution analysis by ICP-MS or ID-TIMS, and multiple mineral fractions are used to construct isochrons. And then there's in-situ sampling, which on the other hand is used in microbeam analysis, such as SIMS and laser ablation ICP-MS, and these are commonly applied to incompatible element enriched accessory minerals such as baryite, which we heard, and also zircon for uranium lead isochrons. A third category illustrated in the previous talk, so this involves extracting small volumes of sample at the microgram or nanogram level using mechanical means such as the focus ion beam and probe, and this talk will focus on the micromill. It is important to note that both the in-situ and microsampling methods are less destructive compared to bulk sampling, and these methods preserve the petrographic context. So the micromill, in simple terms, it combines optical microscopy with precision drilling, and drilling patterns are defined in microscope view field. So it's possible to select what to extract based on spatial information such as petrography and texture. So shown here on the right, I'm not sure if you can see my cursor, but anyhow. So this is the instrument we have at the University of Alberta. The optical microscope is connected to a video camera, which is then connected to the computer. And to the side is the high-speed milling assembly that can be used with a variety of precision drill bits. So for its ability to drill according to spatial information, the micromill has been used for geochemical and isotopic studies of chiefly zoned materials, so such as carbonates and feldspars, and as well as age dating using rare earth element bearing minerals such as garnet and eudialyte, so on. And in addition, there's also stable isotope applications and even metal isotopes in certain meteorites. So given the variety of these applications, this study aims to assess whether or not micromill sampling can be applied to extracting major minerals and shergottites for rubidium, strontium, and or samarium neodymium geochronology. So here we have the drill setup. The next few slides will give a closer look to how the micromill works. So the sample is placed under the optical microscope, and after drill patterns are defined on the computer, the sample stage then slides over into the drill assembly for excavation. For small volume extraction, the sample powder is collected in a droplet of molecule water, and that's placed right over top the sample area. And in order to keep this molecule droplet in place, the sample is actually covered beforehand with a sheet of parafilm with a hole cut in the middle. So after drilling is complete, the sample slurry is then pipetted into a weighing boat to be dried down before weighing and dissolution. The micromill is compatible with many types of precision drill bits, but in this study, we're interested in how small exactly this drilling can go. So we've chosen the conical tipped tungsten carbide bits, which have a small tip angle, shown here on the left in the SEM images. On the close-up on the right, we see that the very tip measures right around 30 microns in diameter. And then subsequently, we can use the scale bar to calculate how much the drilling diameter is at various drill depth, because we'll need to know how big of a horizontal footprint we're leaving on the sample when drilling at certain depths. And here's a look at the user interface. There's a system checklist for calibrations. And this snapshot shows an array that's just been excavated and a second array that's just been plotted. So since we're using a conical tip that's quite sharp, drilling is actually done in singular holes instead of scanning around in order to prevent breaking the tip itself. And on the pattern properties dialog box on the right, so the user can define physical parameters, such as the spacing between each hole, the number of passes, depth increments, and drill speed, drill time, so on and so forth. So note that in order to create open cavities like this using a cluster of single drill holes, the holes are actually plotted so that they overlap a little, just to make sure the material in between actually gets milled out as well. So to assess if micromill sampling can be applied to shergottites for for rubidium, strontium, and samarium neodymium geochronology, the following factors are listed. The minimum required volume to make up one fraction is defined by the minimum mass of strontium and or neodymium required by the analytical instrument. And also it's dependent on the mass of these elements in the target mineral that's going to be drilled. Then we assess how these minimum volumes translate into drilling time and also the sample area that's required. And then we compare these to the actual petrography and textures of shergottites. So here we estimate the minimum required volumes. It's quite a large number, some numbers over here, but essentially we estimate the amount of pyroxene, plagioclase, olivine, and marlite required to return around 1 nanogram of strontium or 1 nanogram of neodymium. So the calculations are based on these estimates, so these constraints. And the first column here lists the literature value of these concentrations in shergottites. And we take the upper limit, so because we want a minimum estimate of the required volume, so we take the upper limit of these values and arrive at the minimum required sample mass. And then we use the density of each mineral to convert that into minimum sample volume needed for each mineral. So that I want you to focus on is these numbers here at the end. So overall, the minimum required volume for each mineral for strontium isotope analysis is in the order of 10 to the power of 6 or 7 cubic microns, while for neodymium analysis, the volumes are generally higher, so 10 to the 8th to 10 to the 9th even. And to give that, so that's approaching, well, that's beyond 1 cubic millimeter in that case. So based on preliminary drilling of non-meteorite samples that we've done so far, we determined that it takes about half an hour to excavate about 10 to the 7th cubic microns of material. So that translates into this plot of drilling time versus strontium levels in the target phase. The thickness of a blue curve accounts for the density range of the 4 minerals. And the gray bars here show the literature range of strontium levels in the minerals. Essentially, the higher the strontium there is in the target phase, the less we'll have to drill out in order to get enough strontium for one analysis, and that means shorter drilling time. And for reference, the red dashed lines here represent 1 hour to 2 hours of drilling time. So looking here, we see that the minimum required volume for plagioclase and marlite can be milled out in under an hour. However, pyroxene and olivine, which have a lower strontium concentration, would take much longer to create one fraction. And only pyroxene compositions with really with around 10 ppm strontium would take under 2 hours to extract. So these are estimates for rubidium strontium work. So keep in mind on the last slide that the minimum required volumes for samarium neodymium analysis are an order of 2 magnitude higher than these. So that demands almost unrealistic amount of both time and sample. So for the rest of this talk, I'll focus on the estimates for rubidium strontium. So to show how the minimum required volume translates into actual footprints, we assume a drilling depth of 50 microns and then compare the resulting area needed with actual shergotite petrography. So in this case, NWA 10299, which is a enriched basaltic shergottites. So for reference, a single 50 micron deep hole will also be around 50 microns in diameter. So plot over here. For plagioclase, the minimum area required for drilling fits well within this grain. So this is just to provide a visual comparison, and ideally, the mineral compositions in a sample will have to be surveyed beforehand to estimate exactly how much drilling is required to get 1 nanogram of strontium. For marlite, the minimum required volume is similar. However, marlite grains in this image are not coarse enough for micromill to maneuver without drilling into the neighboring phases. Also, as illustrated in previous talks, there are fractures and inclusions and of other late stage phases. These inclusions can affect the analysis by shifting the rubidium strontium ratio. And the challenge with fracture is that, as James brought up, is that so these can be a sign of the shock that these grains have been subjected to. So these fractures carry alteration products or shock veins, then the isotopic signature will be disturbed, making it difficult to interpret the isotopic data. So likewise for pyroxene, so while there are definitely grains coarse enough to support the minimum required volume over here, it's difficult to sample a grain without drilling into fractures. And in addition, the minimum volume requires drilling from the most strontium-rich compositions. And typically that means these light colored regions on the rim, and which crystallize late during magma cooling, so which means they have a more evolved composition. But this also means that these evolved pyroxenes are commonly associated with other late stage phases. So like illustrated over here. So phosphates, iron sulfides, and also glass and mesostasis. So if these additional phases are encountered while drilling for pyroxene, the isotopic signature will be also disturbed by these phases, which can commonly have much higher strontium content than the pyroxene itself. Alternatively, if we were to drill only pyroxene cores to be on the safe side, then these have much lower strontium levels, and we'll need to find tens to hundreds more grains like this shown here to create 1 pyroxene fraction for rubidium strontium analysis. So all this means a larger footprint across the sample. So now let's come back to the feasibility assessment chart. We identify the following challenges with micromilling shergottites. The minimum required volume can take longer than 2 hours to extract, and depending on the concentration of analytes in the target mineral, the realistic required volume could be many times larger. With respect to silicates, doing samarium neodymium analysis will require tens to hundreds times more sample volume than for rubidium strontium, and that makes micromilling impractical. And the large required volumes are further complicated by the need to avoid inclusions, alteration, and shock features. When compared to average shergottite grain sizes and the scale of these heterogeneous features, the minimum drilling diameter of approximately 50 microns will have a hard time drilling out the required volume while ensuring the purity of the excavated material, unless the sample is very coarse and that every drill hole is carefully placed instead of wholesale drilling. And this will not only result in long instrument time, but also a large footprint where multiple sample sections will be needed to extract enough material to create an isochron. So in summary, we conclude that micromill sampling shergottites for rubidium strontium and samarium neodymium age dating is limited by the required volume, time, the scale of pristine areas available for sampling, and the resulting footprint. Based on these factors, we find that micromilling has no decisive practical advantage over bulk or in-situ methods for shergottite dating. Thank you. I'm happy to take any questions.
Thank you, Alex. Any questions, comments for Alex?
I think someone raised their hand.
Oh, yes, Arshad, go ahead.
Thanks, Alex. Nice work. I just wonder, you can improve on drilling time if you can use a different bit, because usually this kind of bits are good for carbonates or alternates, but we're working on hard minerals. So maybe if you use a different bit tip, you can get a lot of improvement in the drilling time.
Yes, that is definitely taken into account as well. So just to provide a bit of context for those who are not, other people might not be familiar with micromilling, the majority of studies out there in terms of geological, so earth science applications use mills that typically puts a hole around several hundreds micron wide. So that's so in this study, we used the conical tipped ones just to see, I guess, like how high of a resolution we can get, and then comparing that to, whether or not we can we can use that to bypass these physical heterogeneities that's pretty common in shergottites. So in my opinion, if we were to use, say, like a ball mill, which could be tens to 100 times microns in diameter, then we'll have a harder time bypassing, say, these phases that we might need to avoid in order to extract a pure igneous signature.
Thanks.
Yeah, thanks. A question, I think, for those who are more familiar with mass spectrometry. I mean, are there any prospects for reducing the, the minimum amount of strontium and neodymium that you would need in order to resolve the isotopic composition below what Alex has estimated here? Any comments on that?
Yeah, that'll definitely be, that's definitely one of the questions I've been considering as well.
I have a comment on that. So yeah, so my question is, I have two questions.
Yes.
So one is how you determine the depth. So what I'm asking is how you avoid, when you determine the surface of the section, you know where you're hitting, but how much deep you are drilling.
Right.
And so how you avoid you are accidentally hitting different phases with it. For example, when you want to analyze pyroxene, you definitely don't want get any tiny phosphate in it.
Right.
Because you will just drag down on the isochron. So how you determine the purity of the sample, especially when you're talking about so little sample.
Yeah, so one thing I also wanted to highlight, here's the uncertainty in the Z in the vertical direction, and which is one of the reasons why in terms of drilling for isotopic analysis on this scale, the drilling depths are usually pretty shallow, and in some more extreme, well, not extreme, in some more precise method studies, what they've done is every time, so they would use, say, like 5 micron depth increments per session. So, and then so they would mill out 5 microns and clean that up, or collect the sample, clean up the sample section, and then put it back on the microscope to see whether or not they hit something they didn't want. And so that's one, I would say, one way to do it, which will be quite meticulous. So that essentially, while it can ensure sample purity, it also increases the amount of time required to drill out a fraction. So I think the Z direction, so uncertainty in the vertical direction, is definitely a standing issue when it comes to micromilling at this scale.
Okay. Yeah. So the second one is that what's your plan of after you drilling those sample? Well, so usually what we do is, just a traditional crushing, picking, those things. Your limit is, for example, when we are doing a lutetium hafnium oxide, we just measure like a few milligrams. That's really little for us because, one, you need to weigh those precisely. It's not critical because if we are talking about isoclone, you can just do the ratio, right?
Right.
So it doesn't need to be a perfect, but still you need to weigh, you need to spike, and you need to digest. So do you have a capability of you can get that low of the amount?
So that's one thing we're trying to test right now.
Okay.
But so far I've done some drilling work for a colleague for terrestrial igneous melt pockets. But in that case, we're talking about millimeter sized or even to centimeter sized melt pockets. So we had a lot of space to work around. So in those cases, we're looking at, I would say, hundreds of micrograms of material that gets drilled out. And so should probably just flip back to the estimate here. So the estimate here, it's definitely a lot lower. Much larger than that. So you'll need quite a few micrograms out of these as well. The one thing that puts the micromill in disadvantage, in my opinion, is that you can't clean the sample after you've extracted them.
Right.
Because these are essentially powder that are at such a small volume that you can't see them any further as you would do in bulk sampling methods. So basically what you drill is what you analyze. So I think
so you're really reliant on the spatial, the ability to spatially resolve those and make a pure fraction from the drilling itself. Yeah. We should move on to the next talk, but thanks very much, Alex. That was interesting.